Lesson 6 deals with exponential functions. We have spent a lot of time in this unit focused on exponential expressions, simplifying those expressions, following the rules of exponentiation. And here we're actually going to be evaluating these exponential expressions as they pertain to the functions rule. All right, so we're going to be doing some graphing. Graph paper is a helpful thing to have. Obviously, in your packet, the examples have coordinate grids already drawn for us. We are going to be making tables of values based on these exponential functions. There's a couple of restrictions here. When we have this form y equals a times b to the power x, we need to know that a cannot equal 0. If a is equal to 0, this is just y equals 0. And so that is not exponential in nature, regardless of what x is. If a is 0, then this whole thing is going to equal 0. That's just a horizontal line. B is greater than 0. Actually, make this amendment in your notes. It doesn't have this phrase in there. It needs to say b is greater than 0, so pencil that in the notes. And then b is also not equal to 1. So it can go from 0 to almost 1, skip 1, and then go bigger than that. And x is a real number, all right? And so here are examples of what that looks like. Here a is equal to 0.5, b is equal to 2. Here a is equal to 1, and b is equal to 1/2. Here a is negative 2, and b is equal to positive 3, all right? And what we would do is we would have several different values for x, and we would evaluate these numerical expressions to find out what does y equal when x is a positive number, a negative number, when x is 0. X could be anything, all right? And so we're going to put different numbers in here and evaluate what this is using our trusty handy-dandy calculators, all right? If you have one of these calculators, that would be obviously to your benefit, but this one is sufficient and will work for our goals today. So here is our first one. Graph each exponential function, making sure to put all of these points on the graph, all of these x comma y. So remember, we have an x-axis, we have a y-axis, and we might have to adjust the scale. So what that means is that this might not be 1, 2, 3, 4, 5. We might have to make this go by 10s or maybe count it by 12s or something like that, just to make sure that everything can fit onto this picture. So when we have y equals 3 times 2 to the power x, we're going to take 3 times 2 to the power negative 2, or 3 times 2 to the power negative 1, or 3 times 2 to the 0, or 3 times 2 to the 1, or 3 times 2 squared. And so what we find out is that doing this operation, we get to do a little bit of basic computation to make sure that we can follow the rules of arithmetic, applying these powers as needed. We are probably pretty okay with these positive exponents. But remember, when we're dealing with negative exponents, we are creating fractions, all right? Here, it's okay to use a decimal instead of writing 3/2, write 1.5. We're graphing, and so 3/2 is maybe more difficult to graph than 1.5, all right? Over here, this is 3 times 1 over 2 squared, which is 3 times 1/4, which is 3/4, or 0.75. All right, so we have 0. Here, I'll write this in purple. That's helpful, so we can see those a little bit more clearly. We've got 0.75, we've got 1.5, we've got 3, 6, and 12. And so we're going to plot this x comma y, x comma y, x comma y on our coordinate grid. 0, 3, 1, 6, and then 2, 12 is going to take us off the grid here. Notice how I didn't adjust my scale, and so that means that I'm coming off of the picture. All right, that might be okay if we're just guesstimating where this is going to fall. As we work backwards, at negative 1, it's 1.5. At negative 2, we said it's 3/4, 0.75. We can go back farther and farther if we want to, but right now I'm just going from negative 2 to positive 2. And what we're going to find is that this expression will never touch 0. It will never touch 0. It will get closer and closer and closer to 0 without actually touching 0, all right? And so it looks like it kind of levels off here. It doesn't become horizontal, but it looks like it gets to be horizontal as it gets closer and closer as it approaches 0. Now this fancy thing right here, this line that it does not touch, is the x-axis. In this case, it's y equals 0, and this is what's called an asymptote. That's a fancy vocabulary term that says, hey, the graph gets really close to that line, but it doesn't actually touch it. Kind of like, if you have an older brother or sister and they used to get in your face and be like, I'm not touching you, I'm not touching you. And you'd be like, get away from me. It's kind of like what the graph is doing to that asymptote. It is getting very close to it, but it is not actually touching it, okay? It's probably bugging it though, right? And so we want to make sure that we understand where that horizontal asymptote, y equals 0, because y will never, ever equal 0 here. It will get closer and closer and closer to. But if I have a really big negative number exponent, if I have 2 to the 10th, to the negative 10th, if I do 3 times 2 to the negative 10th, that's 3 over 2 to the positive 10. And 2 to the 10th is a really big number. Let's find out what that is. Whoops. 2 to the 10th is 1,024. So 3 out of 1,000 is really small. Really small. All right, 0.00292. So it's effectively 0. It gets really, really close to 0, but it doesn't actually touch it. All right, kind of a strange scenario here. And so that's what we're going to think through and explore. All right, let's do the next one. Here we have 24 times 1/3 to the power x. 24 times 1/3 to the power x. We're going to think with our calculators here, think with our brains as best we can. We're going to take 24 times 1/3 to the negative second, 24 times 1/3 to the negative 1, 24 times 1/3 to the 0. Oh, I know that one. That's 24 times 1, which is just 24. This is 24 times 1/3 to the first power, which is 24 times 1/3, which is 8. This is 24 times 1/3 squared, which is 24 over 9. 24 over 9, which is approximately equal to, let's find out what that is. 24 divided by 9 is 2 2/3. All right? With a -1 exponent, remember, that means that we are going to have the reciprocal. All right? This is 24 times 3 squared, or 24 times 9. So these numbers get really large. 24 times 3 squared in our calculator is 216. 24 times 3, so that's 72. 24 times 3, yeah, Mr. Hibbett, come on, what are you using your calculator for? All right, so now we can fill in these values, and we can probably recognize, understand that, we may need to use a different scale here, because if I have to graph these numbers on my y-axis, these numbers are too large, all right? So if we have 10 spots and we need to get up to 216, maybe each spot is worth like 20 or something like that, all right? Maybe each spot is worth 20. So we're going to count by 20s. So we got 20, 40, 60, 80, 100, 120, 140, 160, 180. This is 200, and then there's going to be 220 up there. So I know that's a little bit awkward to think about that scale, but what we're going to find out when we use that scale is that when I go over to 2, I'm at 2 2/3, which is really close to 0. When I'm at 1, I go to 8, which is only about halfway up, not quite halfway because that would be 10. At 0, we get 24. At -1, we get 72. 72 is going to be about right in the middle there. At -2, we have 216. All right, so when I'm counting by 20s, look what happens to my graph. It's really steep. It's facing the other direction. It gets really close to 0, but this thing will never, ever, ever equal 0. It gets really close to it, but that is our horizontal asymptote. All right, is at y equals 0. It gets really close to 0, but it doesn't actually ever touch 0. All right, so we adjusted the scale so we could draw that graph. I forgot to put the arrow over here. You'll notice that we had a fractional base, which means that as x gets larger, this gets closer and closer to 0. As x is negative, it gets taller and taller. All right, which is flipped from what the last picture looked like when we had a non-fractional base value. All right. Ooh, a negative a value. A here is -1. B here is +2. Let's see what that looks like for us. All right. So I have the opposite of, or -1 times 2 to the -2. I've got negative 1 times 2 to the negative 1. I've got negative 1 times 2 to the 0. I've got negative 1 times 2 to the 1. And I've got negative 1 times 2 squared. This is negative 1 times 1/4, which is negative 1/4. Here I have negative 1 times 1/2, which is negative 1/2. I have negative 1 times 1, which is negative 1. I've got negative 1 times 2, which is negative 2. I've got negative 1 times 4, which is negative 4. So these are my x comma y's, and you'll notice that all of these are negative, but none of them are 0, and none of them pass 0. I'm going to leave my scale as it is. At negative 2, I go down only about 1/4. At negative 1, I go down only about 1/2. At 0, I only go down negative 1. At 1, I go down 2. At 2, I go down 4. All right? And we can make predictions about what's going to happen at 3. We're going to have negative 8. At 4, we're going to have negative 16. All right? Over here, we're going to keep moving closer and closer to 0. So we can make some predictions. We can use our calculator to see what that's going to look like. But you'll notice that this one is a negative. It's pointing down in the negative direction. It's kind of like almost the inverse of what we saw before. We still have this horizontal asymptote at y equals 0, and we want to acknowledge that. So creating a table of values with our x comma y's is how we do the graphing, all right? That is a drawn-out process that is going to require that we use our calculator. Now, I executed some of that multiplication on my own. You can use a calculator as much as you need or want to, all right? If you can do it in your brain, then that's obviously awesome. When we are dealing with a when we're dealing with a b value that's bigger than 1, that means that the graph is going to be growing, and it's growing exponentially, which means it's not growing in like a linear fashion. It is growing at a very rapid rate, all right? If you look at the graphs in recent days with the coronavirus testing, you'll notice that there's a big spike right now. We flattened the curve, right? It's like flat vertical. That's not how it's supposed to go. But you'll notice that it amplifies, right? It escalates. It gets a lot larger, faster. There's a lot more cases. As more people have cases, it spreads faster, all right, to more people. That's called exponential growth. When b is less than 1, but specifically greater than 0, pencil that in there too. B has to be bigger than 0 anyway, but if it's between 0 and 1, that's a fractional value, that's a decimal. So it means that at every iteration, it becomes smaller. At the next one, it gets smaller. At the next one, it gets smaller. At the next one, you're multiplying by b again, because that's how exponential relationships work. When you have b to the x power, you start at b, and then if x is bigger than b, if b is bigger than 1, then you're multiplying by a number that's bigger, and so it's going to steadily get larger and larger and larger. If that number is less than 1, you're multiplying by a fraction, so it's getting a fraction as tall as it was before. So you'll see that these go like that, and these go like this. Now, if you have a negative a value, it'll go down. If you have a negative a value here, it will do the same thing. It'll still go this direction, but it will be opposite, right? It's the opposite of, all right? And so we want to consider that. We want to think through that as best we can. But the goal there is to make sure that we are covering our bases, right? That we're understanding growth versus decay. Growth versus decay, all right? And so determining whether this is growth or decay, we are going to look at that b value. B equals 0.12, A equals 100. This number is irrelevant to the conversation. If we're talking about growth or decay, we're going to look at this. This number is less than 1, therefore this is exponential decay. 3 over 2 is B, and then this number is bigger than 1. 3 over 2, the numerator is bigger than the denominator, so this is an improper fraction. It's bigger than 1, so this is exponential growth. All right? Do these two. All right? Find out what B equals. Find out what B equals. Is that number bigger than 1 or less than 1? If it's bigger than 1, we're dealing with growth. If it's less than 1, we're dealing with decay. You do these. C and D. All right. Pause the video if you need more time on those two. And then let's address this real world connection here. As we work through this, we want to obviously apply and understand how this relates to the real world. And so here's the situation. You've decided to become a crazy rabbit person. Imagine that. It's better than maybe a crazy cat lady, but whatever. Crazy rabbit person. You buy 20 rabbits for your farm. The population of the rabbits on your farm triples every 6 months, every half a year. The function f of x equals 20 times 3 to the x models that situation. How many rabbits would there be after 2 years? After 2 years, all right? It triples every 6 months, every half year, all right? So we started with 20, and we triple every 6 months, all right? So x equals the number of half years, all right? So in 2 years, how many half years is that? How many half years is that? And so in 2 years, you're going to have a half a year and another half year makes 1. Another half year and another half year makes 2. So that is 4 is what x is going to equal. So how many rabbits will there be? Well, y will equal 20 times 3 to the 4th power. Y equals 20 times 81. All right? When you use your calculator there, you find out that you get, what, 1620? 20 times 81 is 1620. 1620, this is a real world connection, so it's not just a number, it's a number of something. 1620 rabbits, all right? It's a lot of rabbits, and so obviously, a crazy rabbit person. So that kind of gives you an idea of how we would use and apply these exponential functions, all right? We explored that a little bit in lesson 1. But what happens after 3 years? What happens after 6 months? What happened, or what would have happened if we thought about this in reverse, going back in time if we started with a smaller number of rabbits, etc. And so this kind of gives you a good idea of how we would apply these, this understanding of exponential functions.